Hi everybody, and welcome to the first lecture in our course Exploring Quantum Physics. Today I will introduce the main formulation of quantum theory due to Schrödinger, and I will also tell you a little bit about a fascinating history of the subject. But before going to this main part, I would like to talk about the process of learning quantum physics, and about why I think so many people find it difficult and frustrating. And I hope that this brief discussion will help you avoid this frustration and make the process of learning quantum physics here more effective. Richard Feynman doesn't really need an introduction. He was one of the heroes and legends in physics, universally recognized as a genius. He was also a great speaker and enthusiastic popularizer of physics. In 1979, he gave a series of very interesting lectures in quantum physics at the University of Auckland in New Zealand. They're actually available on YouTube online, and I would encourage you to listen to them. If you do so, you will see that Feynman spends 30 or so minutes in the beginning of his first lecture to prepare the audience for what they were going to hear next. And one of the main messages of this introductory part was that no matter what Feynman were to do, the audience wouldn't really be able to understand quantum mechanics anyway. Then he talks about physics students and physics professors and their level of understanding of quantum physics. Let's listen to what Feynman had to say in this regard.
If I'm going to explain this theory, the question is, are you going to understand it? Will you understand the theory? When I tell you first that the first time we really thoroughly explain it to our own physics students is when they're in the third year graduate physics, then you think the answer is going to be no. And that's correct. You will not understand. But this business about not understanding is a very serious one that we have between the scientists and an audience. And I want to work with you because I want to tell you something. The students do not understand it either. And that's because the professor doesn't understand. Which is not a joke, but very interesting.
So what Feynman seems to be saying is that nobody, not even professional physicists, not even himself perhaps, really understands quantum physics. Well, this is probably the last thing you want to hear before starting this course. But this is certainly not my intention to give you the impression that you should give up without even trying. On the contrary, I'd like to speculate what I think Feynman might have meant there, and about why I think so many people find it difficult to study quantum physics and other advanced physics subjects. And I hope that this discussion will help us further down the road when we encounter unusual counterintuitive quantum phenomena. Let us look at quantum mechanics from the perspective of all major physics theories out there. In this slide, I attempt to present all these theories in a single diagram, which of course is an unrealistic, sort of silly task, and so the result I came up with shouldn't be taken too seriously. What we have here are three axes labeling fundamental physics constants. So here I have the inverse speed of light. This constant g is the gravity constant, which appears in the Newtonian gravity. And along the horizontal axis I have the Planck constant, which, as we shall see, is the most important fundamental constant that appears in quantum mechanics, in that it relates the particle and wave properties. Now, the red dots in this diagram represent symbolically major fields of physics. For example, on this line I have two red dots, so the one which has all corresponds to all physical constants being zero is just kinematics or classical mechanics, essentially 17th century physics. So this dot here with the finite gravity constant but all other constants zero is the Newtonian gravity. Now, moving up the vertical axis to a finite speed of light brings us to a theory which takes into account this finite speed with which interactions propagate, and this is the celebrated special relativity theory of Einstein. Combining it with gravity results in general relativity, another very famous geometric theory of Einstein. Finally, moving along the horizontal axis to a finite Planck constant brings us to actually the subject of our course, non-relativistic quantum mechanics. So there is also this part, which we're not going to discuss too much in this course, which combines the relativistic effects and quantum mechanical effects, and this is so-called quantum field theory or quantum electrodynamics, a more complicated theory. Actually, I could have added here another dot, which has all fundamental physics constants. This would be a theory of everything. It doesn't really exist yet, but everybody wants to get it, so this has been one of the holy grails of physics for many years. Now, going back to learning quantum physics and what does it all have to do with it, so let us discuss what theory governs our everyday lives. What is sort of our comfort zone? And I would claim that we are somewhere here in this area. Certainly, the length scales that we encounter in our everyday lives are much larger than atomic. The velocities are certainly much smaller than the speed of light. And, well, we do experience gravity on a daily basis. So we're somewhere here. And here is also where our intuition works. And if we say we understand something, what we usually mean by that is that we can relate a phenomenon to another phenomenon that occurs here in this area. So for example, if we were to say that we really understand a quantum mechanical effect, it would oftentimes imply that we have found a way to relate it by something that we already know here. But the problem with all these advanced physics subjects, especially with quantum physics, is that such a mapping, such a relation is not always possible. In other words, it's not always possible to meaningfully project quantum mechanical phenomena onto this classical axis. And if no classical analog exists, this is what we call strange, and this is what we find difficult. But on the other hand, if we were to imagine a fictitious civilization of tiny species that lived on atomic scales somewhere in this area, so these guys would have had really a lot of problems understanding our classical world. So the problem is not really with the quantum physics itself, but with our centristic position on how we want to understand it. But now, how do we learn quantum physics if we can't really readily understand it at intuitive level? Fortunately, there is a way to do so. By speaking a common language of all physics theories that is not rooted in and is independent of our classical world. And this is, of course, mathematical formalism that needs to be developed. And it may turn out that two seemingly unrelated phenomena, let's say on the classical side and on the quantum side, may be explained by similar differential equations or something like that. And by studying those, we can develop intuition about something which is otherwise inaccessible to us. But after this discussion, you may ask, why bother studying quantum physics if it's not really relevant to our everyday lives? So the motivation comes from experiments, and more recently also from technological advances that create systems and devices which operate further on the right on this axis. The take-home message here is that when you study quantum physics, or any other advanced physics subject for this matter, you should actually be prepared to encounter phenomena that may appear bizarre at the first sight, and that you may find difficult to understand. When it does happen, don't panic, and certainly don't drop the course because of that, and don't assume that others find these things obvious. It's certainly not the case. So I think the best way to understand such new concepts is first to understand experimental data that support them, and then develop or understand the mathematical formalism and the appropriate theory that describes these phenomena. So when you use this theory again and again, you will develop your own intuition and get a feeling about a deeper understanding of the subject. So speaking about the mathematical side, so I should mention that of course quantum mechanics is a demanding subject, and we will have to use certain advanced mathematical techniques. But there will be lectures with different sort of levels of mathematical sophistication. Some of them will be pretty advanced, some of them actually won't use much math at all. And so I hope that all of you with different backgrounds and different levels of mathematical preparation will find something that is useful and interesting.